All right, so we'll just pick this one here. What we're going to do is we're going to perturb it. There are different ways. I mean, we could add water to this side. We could add water to this side. We could remove water from this side. We can remove water from this side. And so removing or adding water just equates to increasing or decreasing the concentration and or pressure. And so we'll just do one scenario here. We're going to just add more reactant. I.e. increase the concentration or increase the pressure of the reactant. And so originally it was at this level, and so this is the original equilibrium. And so if I add additional water to this side, let's say I add this much here. And so this is my perturbation. So I'm going to perturb the equilibrium, that is, upset this by adding water here. And what that's going to do is it's going to shift it. So rather than having equal rates, I'm going to shift it so there's going to be a net transfer here. The rate forward is greater than the rate reverse, so I got a net forward. And what's going to happen is we're going to reestablish equilibrium. However, the equilibrium is going to be different than the original equilibrium. And so what's going to happen to the left side? Well, the left side is going to do two things depending on your initial frame of reference. If your initial frame of reference is here, then what happens to the left side is this. It goes down. Right? If your initial frame of reference is the original equilibrium, then it goes up. And so, you know, what's going to happen, let's figure it's going to be somewhere here, you know, in between the high mark here and the high mark here. Right? And so you have to read the question carefully. Sometimes what they ask you is what happened to the reactant compared to the initial equilibrium. Sometimes they'll ask you what happened to the reactant compared to the perturbed equilibrium. From the perturbed it goes down, from the initial it goes up. Okay? On the product side it just goes up, right? Because the perturbed, the initial here and the perturbed the same, and so we end up at a new equilibrium here. And so this is the new equilibrium established, and the new equilibrium is going to be different than the original equilibrium. However, the ratio should be the same. You know, we should end up at the same ratio, and so in that sense, they're the same because we'll have the same product. You know, K didn't change. We'll still have the same product to reactant ratio at this particular temperature. However, the concentrations did change, or the pressures did change. All right, so we can just see what's going to happen. You know, quickly here, let's look at all the possible scenarios for Le Chatelier's. All right, one is the concentration. You know, if we look at the reactant concentration, if the reactant concentration goes up, then there's going to be a shift here. The shift is going to be to the right. If the reactant concentration goes down, then there should be a shift left to reestablish. So that's like removing water from this side. The same thing, if the product concentration goes up, we should shift left to decrease the perturbed concentration product. If the product concentration goes down, we should shift it right. All right, the pressures are the same. You know, because pressure and concentration are directly proportional to each other, and so pressure shows the same behavior. Essentially, just increasing the partial pressure of the reactants is like increasing the concentration. Decreasing is like decreasing the concentration. So we expect the same shift. And so we just say pressure of the reactant goes up, etc. There are some more things that will perturb the equilibrium. Volume. Well, actually, I need to say one more thing. This is increasing the pressure of the reactant or the product. But if we change the pressure by the addition or removal of inert gas, then no impact. There should be no shift in the equilibrium. An inert gas would be, what would be an example of inert gas? If we look at this reaction, 2NO plus, well, this is a very simple reaction. We'll just go 2NO gas goes to N2O2 gas. And so we're going from nitrogen monoxide, and we're going to connect those with this kind of dimer type of structure here, dinitrogen dioxide. If I add some gas like argon is a really inert gas, or maybe nitrogen. You know, does nitrogen participate in this equilibrium? So if I add argon, does it bump up the reactant or decrease the reactant pressure? Or does it mess with anything over here? No, the same thing with nitrogen. Inert just means it does not participate in the reaction as written. It could be any gas, whether it's a real inert gas like argon, which is also called a, what are the inert gases known as? The Nobel gases. It's something I don't really emphasize in Chem 4, Chem 1A, but maybe I should, because people. Anyway, N2 would be considered inert in this scenario. O2 would be considered inert, but O2, there could be potential side reactions that occur, so we got to watch out for those. Other than gas, then no impact on equilibrium, but total pressure increases or decreases. And so, yeah, P total, because the P total, you use Dalton's law and just sum up all the partial pressures. However, if we change the volume, then we're going to have the same number of moles, but compressed into a smaller volume. And so, if we change the volume, that will have an impact. And so, the easiest way to see the impact, well, one way is you could just look at calculating the Ks and with different volumes and see how that changes. But the easiest way to see about the impact of volume is this. If we increase the volume of the entire system, then this favors the side with more moles of gas. Now, if we have a solution, then we take a look at how the solution concentrations are impacted, and it's the same type of scenario as the gases. Okay, for solutions, the volume change will change the molarity, which is going to upset. Now, normally you think, well, if it's a solution, it should change the molarity of both, the reactants and the products, the concentrations. And the same thing here. If it's a gas, it should impact both. So if I double the volume, shouldn't both the reactant gas pressures and the product gas pressures decrease by half? Yes, they should decrease by half. And if they both decrease by half, shouldn't the impact cancel itself out? The only time it cancels itself out is if the number of moles of gas on the left equals the number of moles of gas on the right. If they're mismatched, then they don't cancel each other out. And there is an impact on the volume. The volume is going to cause it to shift. So even though I'm doubling the volume for both reactants and products, it could shift or might not shift. It depends. If it's an equal impact on. And the same holds true for solutions. If you have the same number of moles of aqueous solution on the left. On the right, then doubling the volume is going to have no impact because it's going to cancel out. However, if it's different, then it's different. And so this is the same type of scenario that we looked at yesterday when we write K. When we write K, we use molarity. Molarity to keep us safe. We can use moles rather than molarity, but only when volume doesn't affect K. And when does volume not affect K? The only time volume doesn't affect K is when the number of moles of gas on the left equals the number of moles of gas on the right, and the volume cancels out, and therefore there should be no impact on the equilibrium with a volume change. But when they're mismatched, then there will be an impact. And so here, yes, increasing volume favors the side with more moles of gas. If both sides have the same number of moles, then no impact. Decreasing volume favors the side with fewer moles of gas or fewer moles of aqueous solution. Now, there's one more thing that's going to do a Le Chatelier's shift, and that is temperature. But temperature operates differently. The way temperature perturbs, these are all Q perturbations. You know what I mean by Q? Q is just your given, your given ratio. Q is, this is the ratio you're given. Is this ratio even close to K, the equilibrium ratio? Or sometimes Q is bigger than K, which means we have too much product. Sometimes Q is less than K, which means we have too little product. And sometimes Q is equal to K, which means we're at equilibrium. I mean, the ratio is already at equilibrium, so we don't have to do anything. There's no driving force. And so these types of things are just changing Q. Hey, we were at K. We were at the right ratio, but now I screwed up the ratio. And since I screwed up the ratio, then I got to reestablish that ratio here to the proper ratio. It didn't change K. However, temperature screws up the ratio, screws up K. And so temperature alters K and causes the original equilibrium to no longer be good. And so I could not even touch this. For example, I could not even touch this here. Just leave it alone. I'm not going to add any water. I'm not going to remove any water. All I'm going to do is I'm going to change the temperature. And if I change the temperature, all of a sudden, it changes the well size. And so let's say this well size grows bigger and this well size goes smaller, and now I got too much water on the left, too little water on the right, and it's going to have to change. So this temperature alters K. Therefore, your original equilibrium is no longer going to be an equilibrium. You have a new ratio you have to adjust to. And okay, that's fine, because we can calculate K at different temperatures, right? And so if we screw with the temperature, let's figure out the new ratio that it should be. But we don't have to do that in Le Chatelier's qualitative. In quantitative, we would do that. But for just qualitatively seeing what's going to happen, then it's going to be like this. Increasing temperature, and this is going to be just simplified. Increasing temperature, you know what increasing temperature does to the K? It depends if it's endothermic or exothermic. Because endothermic would be positive delta H, and exothermic would be negative delta H. So it does opposite things depending on. And so increasing temperature favors endothermic or exothermic direction. Endothermic. Yeah, and the way I always remember this is ice. Melting ice is endothermic. And so do you want to increase temperature or decrease temperature to melt ice? You want to increase the temperature. Decreasing temperature favors exothermic. And so yes, we could calculate K, but we could save a lot of time. We could save a lot of time, but just looking, if we just want to do a qualitative prediction, we could save a lot of time just by looking. If we want to do quantitative, then we're going to have to recalculate our K value at the new temperature and then redo our ice calculation. Redoing our ice calculation, that's what we're going to do on Monday. I'll show you how We'll do this qualitative today, and then on Monday we're going to start quantitative. That is doing calculations to see how Le Chatelier's is going to screw up our equilibrium, our original equilibrium, and how it's going to change. All right, so the lab today is just this. You know, sometimes we don't need a lot of solution. Do you guys have spot plates in your drawer? Spot plates? Spot plates are these porcelain plates with little dishes, bowls in them. And the spot plates, you could do a series of reactions in a spot plate with very small scale. That's it, right there. Jackie has it. That's a spot plate. We use spot plates or test tubes. We don't have to be very careful with the measurements. We just want to see. We have an equilibrium situation. We're going to add something to it to upset the equilibrium and see if there's visible changes to it. And sometimes there's visible changes because the reactant and the product are different colors. That's the easiest, or something else. Maybe one is endothermic, the other is exothermic, etc. All right, any questions on today's lab? So we're going to do different things. We're going to add more, add less. You know, that is bump up the concentration, bump down the concentration. We're going to change the temperature to see how that's going to shift the equilibrium. And we're going to look for visible signs because everything that we're going to look at right now is already at equilibrium, I think. And so we'll just see from there. And the reactions are given in your note there in the lab manual. All right, I'm going to stop talking here and let you guys work on the lab now.